Thank you, Paolo. So we are moving now to panel 8 on spectral distortions. And you are starting now with Jens Kluber on exploring new horizons with CMB spectral distortions. By the way, the order of the panelists' presentations has changed.
Yeah, and I found out just now, so the talk, although the slides were ready already on Monday, has changed in my head like multiple times in just this minute as well. Anyway, yeah, it's a great honor and pleasure to be here, and thanks a lot for having me and inviting me. And yeah, I'm going to try to tell you a little bit about spectral distortions, and I'm sure many of you have heard about this a number of times at the CMB 60 meeting. I was looking actually back at the slides, and there were a couple of slides that I found that were very similar, but then there was another meeting in Ferrara in 2022 which updated several slides. So I'm going to give you a little bit of a spiel on all those different steps in the last 10 years. Okay, so first I wanted to remind everyone, of course, we're talking about departures from this black body shape. Kobe has demonstrated that the microwave background average sky intensity is close to a black body with extremely high precision, and there is these mu and y parameters that characterize the departures. I want to pause for a second though, because this number, T0, we never really mention, Lyman was just showing the 6 standard parameters, we never really mentioned T0 as a parameter, but it is one of the cosmological parameters, and indeed, this determination is, back in the days, was the most precise parameter, cosmological parameter that was measured, and aside from theta, the angular scale of the first peak, this is still to date, I think, one of the most precisely measured parameters. So this is just showing you how amazing these measurements were. Okay, and Rashid, of course, already mentioned it in his talk as well. Spectral distortions are caused by energy release and injection, and the classical distortion shapes, the Y distortion and the mu distortion, they go back to the early works of Rashid and Zeldovich, which demonstrated these key signals that you can look for in terms of departures from the black body spectrum. The Y distortion we know in connection with the Sunyaev-Zeldovich effect at low redshifts, but if you have energy release at high redshifts, you get a similar kind of effect. You can get the partial upscattering and comptonization, which is a Y distortion, here with a very extreme Y parameter. If you inject energy early on meaning at a redshift of above 50,000 or so, this is some 1,000 years after Big Bang, you will get a mu distortion because you have the ability to basically redistribute photons and reach a kinetic equilibrium under Compton scattering. So very, very strong comptonization regime. Since these early days, of course, we now understand the physics of distortions a lot better. We very precisely can say how the thermalization process basically erases any distortions very early on. Then how mu distortions in the redshifts between 300,000 and a few million, how the mu distortions evolve and form. We also can treat very precisely the transition between mu distortion and Y distortion regime. There was the question about the intermediate distortion, which is precisely this transition regime, but the information that's actually contained is the so-called residual distortion, which is essentially a nonlinear comptonization correction, and we can get time-dependent information from this. And then we also know how to calculate the recombination process very accurately and get the recombination lines. And in addition, we can now do not only energy release distortion calculations, but we can also consider the distortions produced by photon injection processes, by particle decays in the non-thermal, high energy regime, and we can even treat anisotropic distortions and large distortions. So in terms of real scientific description of distortion physics, we have really a great handle on all those different processes. And this, of course, means that there is a great and unique science case connected with spectral distortions, one of them being that there is guaranteed lambda CDM distortions. I will show them in a second. But then there's also a lot of complementarity with other aspects of our cosmological exploration, probe of inflation, discovery potential, particle physics. There's lots of opportunities here. And of course, this is, target of several experiments. I will show, highlight a couple of experiments in a second. So here are the lambda CDM distortions. The largest expected distortion is coming just from the hot gas in the universe. Part of that is, of course, dominated just from clusters of galaxies at late times, which contribute to the average sky flux. The distortion is at a level of 10 to minus 6, 2 times 10 to minus 6. I'm showing here the real distortion with respect to the black body as a function of observing frequency today and in absolute units. So the null is the 217 gigahertz null from the Sunyaev-Selvidge effect. And because we can dream of making very precise measurements, we can even see the relativistic correction to the signal, just coming from the fact that the gas is actually not just cold or non-relativistic gas. We actually see corrections to this, which is this temperature distortion. And then there's the dissipation of acoustic modes at small scales, which basically are a measure of the amplitude of fluctuations at something like 1,000 inverse megaparsecs. So extremely small scales, and that gives you a mu distortion that we should be expecting at a level of 2 times 10 to minus 8. And then the recombination lines down here. It is really interesting to note, although these recombination lines are the smallest distortion in some sense, they have many, many features. So in reality, the foreground challenge is not as severe in the recombination lines in comparison to the mu distortion. Okay, but that's not all, of course, because a lot of processes can, and people are talking about a lot of processes that could exist in the early universe. There could be all kind of non-standard things. So first of all, the standard distortions are the yellow boxes. So the late time distortion from structural formation, ionization, the cosmological recombination lines, the acoustic waves damping away and leading to a mu distortion, and then also, I didn't mention it explicitly, just the cooling of matter. But people are talking about decaying particles, primordial black holes, primordial magnetic fields, axions, dark photons, cosmic strings. I think everybody who is excited about some new physics can actually find something on this chart. And this is an old chart, which I just added a couple of cases that have now been worked out even more, but there's more opportunity just by thinking about any process that leads to electromagnetic interaction with the plasma. So this slide I already showed, but we also can now demonstrate that there's big synergies with spectral distortion science and other categories of cosmology. So for example, 21 centimeter, we have already heard about 21 centimeter cosmology and all the progress that is planned and that is being made. And the background light that is actually, where the signal is produced is the CMB. But if the CMB is distorted at low frequencies, I didn't use that word when I asked the question because Scott was, of course, thinking that I would ask about spectral distortions. But if you have a radio background, a spectral distortion caused radio background, energy injection, cosmic strings, or so on, you actually interplay with this physics, and that changes your predictions and analysis of 21 centimeter cosmology. So there's a big synergy, which one actually probably will have to explore way more than we are currently have done. And here's just a paper where some of these steps are explained. And then we also, of course, can look just with these experiments that will measure these distortions, we can look for other monopole signals. So line monopoles is one of the things, and Rashid was pointing out, the early universe, redshift 10 universe will give you contributions, and this would be, these are some predictions that are just telling you how much, what's star formation rate density, all these questions that line intensity mapping people are also looking at. And of course, you can have low resolution maps of the sky that explores precisely these kind of line intensity mapping science cases as well. And here's some recent work which highlights this in the context of some of the future experiments.
5 minutes.
And we can do, and that is very stressful, we can do spectral distortion anisotropies, and we can indeed calculate these distortion anisotropies very precisely now. So that is a science case that is also applying to things like Lightbird and any of the imagers we're talking about. Here's a slide that I showed at the Ferrara meeting, and I want to not show the slide because there's so many proposals that haven't gone forward, which is in some sense, of course, a very sad aspect, but it's actually showing that there's lots of activity in the past years. And one of the updates is, of course, that this is 2025 now, not 2022. And there's also one really important aspect, that some of these things are now going ahead. They are not actually fiction anymore. There is activity from the ground. Bizou, most importantly, has been selected as a balloon to phase A, and we're studying it now to, hopefully be flying in the next couple of years. And there's TMS, the Tenerife Microwave Spectrometer, which is, also going to be expecting to be taking data. Alberto Rubino Martin is here as well, if you want to have some more details. And then Cosmo, we will hear about that from Paolo. And there's also one thing that I just wanted to highlight. In Manchester, the weather is bad, but at 1.4 gigahertz, you can actually do absolute measurements. At least that is what Ian Brown and Peter Wilkinson are thinking with LBAS. So they will try to produce an absolute measurement of the sky at 1.4 gigahertz. And then we will hear from Nabila about the fossil M8 proposal that we just put in. So I think the one science case that I want to highlight, and I hope you will give me a slight leeway, is what is the power in terms of measuring the small-scale universe. So this is a figure that Bryce Sear has produced recently, and it just highlights, of course, the constraints on the scalar power spectrum amplitude that we have today. This is a forecast here. This is just the expected fossil level of constraints that you might be getting from mu distortion measurements and also from Y distortion measurements. But the important thing is, at large scales, of course, CMB has really nailed it. We know the amplitude of fluctuations, the scale dependence and everything. There's no wiggle room there. But at small scales, things are much more uncertain. So Phyros is basically a factor of 10 to the 5, 10 to the 6 weaker in terms of the level of constraints. And then you have other experiments that in the future will add constraints or have already added constraints through pulsar timing and all these things. So the important thing is that the small-scale universe is where the uncertainties are. And I think that is a really important indication. And Dick was yesterday talking about a lot of physics that could be related to small-scale physics as well. And I will try to give you a little bit more evidence that we should probably be expecting small-scale physics to play an important role in the universe. And supermassive black holes, for example, is a problem. We don't still know where they really come from. Now, primordial supermassive black holes, they have been ruled out by Phyros, essentially, because the amplitude of the fluctuations is too small to actually allow them to form, okay? So that's ruled out, that path is ruled out, but things like smaller mass black holes then merging and building clusters, and there could be an origin which is related to primordial black hole formation, a seeding of supermassive black holes. So that's a question that, of course, spectral distortions will themselves shed light on. And of course, we have seen these mergers of black holes, which indicate that there might be some early population, probably not all of the dark matter, but there's certainly some aspect of small scales probably contributing. Then we have seen the little red dots, which are just indicating high redshift activity. We have heard from Andrea as well yesterday about the star formation rate being basically much higher than we expect. And we know the arcade excess, which is another thing that I think we should really think about. This radio excess at low frequencies, which has been independently confirmed with LWA as well in 2018, is an indication for some excess activity. We can't explain it by stacking radio sources that we know about, and there could be just like early activity of radio fluxes or some exotic physics. And the Hubble tension. And I think this point is actually one that I want to spend a couple of minutes on if I have, please. Seconds on then, because I think this is a really important aspect. So recombination is a key ingredient in our analysis of cosmology. If we would be changing the recombination history, if we wouldn't, for example, have updated the old calculations of RecFast, we would have been talking about different NS, and I think Andre would have been probably unhappy as well. But we have done, according to standard atomic physics and so on, we have done good calculations that we believe, and those are key in the analysis of our data. However, if you allow for the option that the recombination history is actually varying, you can find that the Hubble tension can be solved, or alleviated at least, with modified recombinations that have that is early. Okay, and modified recombination that's early can be caused by small-scale clumping. So if you had clumps in the universe that are basically leading to patches that recombine quicker, on average you can get faster recombination. And this is work that Gabriel Lynch and Lloyd Knox and I published just right after the DESI data came out in the last year. But the ACT team has now redone this, and here's their reconstruction of the recombination history based on their combinations of data. And you can see that modified recombination scenarios, here I'm highlighting the varying electron mass scenario, which would be assuming that atomic physics is different at recombination. That's not what I'm advocating, but it's actually doing pretty well in getting close to the shoes constraint on H naught. And the modified recombination scenario, if you just compare, early dark energy is something that we're considering all the time. Modified recombination does actually a really pretty good job. Okay? So, I know. But I want to say that there's something missing, which is we haven't actually taken fully into account what clumpy universe means. And I just put out a paper yesterday, well actually 2 days ago now, which is highlighting this, where we basically did a stochastic treatment of a small-scale fluctuating field, and you get a second effect, which comes just from the non-uniformity of the medium. So if you imagine a uniform medium, you have a scattering rate that gives you, according to the electron recombination history, gives you the coupling of photons and pions. If you now organize these into some small-scale clumps, then of course part of the universe is totally empty. And the other part has these enhanced peaks. You don't want to change the average density or anything. You're just looking at reorganizing the structure. And in the density peaks, you have higher scattering rate, and outside you have lower scattering rate. But if you take the ensemble average over the scattering rate or over the physics that describes the transport, you actually get a reduced effective scattering rate. The universe becomes basically transparent. If you really would put everything into delta functions, you have very low probability of meeting those density peaks. And this is what we're now exploring as an additional aspect of solving the Hubble tension, and it might even help better than just changing the recombination history, because it has additional effects that are not degenerate with just changing the recombination history. So the bottom line I wanted to say, I don't have a solution to the Hubble tension, but thinking about the small-scale universe is, I think, really, really important. And I know.
Yeah, sorry.
Okay.
Last slide.
So we need to think outside the box. That's the one slide that I wanted to show. Reno had put that up at the Ferrara meeting, and we have, the box is normally R. We heard N effective. We heard neutrino mass. And outside the box, I think, is spectral distortions. And we should really think about measuring these distortions as part of our future. This is from the meeting in Turin, very similar, a couple of years ago, where we were discussing, indeed, the future of CMB. And spectral distortions, I think, should really be part of the discussion. And I would say that it would be really great if, instead of taking a factor of a few improvements with space, we can just do a factor of 1,000 or more. That would be an amazing thing to do. So I leave you with that.
Thank you, Jen. I don't think we have time for a question, so I ask Nabil Aganim for the next presentation.
Coucou, ça marche.
Okay. Thank you. Thank you.
Yeah, thank you. Thank you all for having me here, and thank you. I want to thank the organizers specifically for inviting me to this anniversary. It's really an honor to be here with you, and it's also a very big pleasure to meet friends that I haven't seen for some time already. So I'm going to present this attempt to lead you towards CMB Spectral Distortions from Space, a program that we're putting together with many people. Many of them are here: Paolo, Jens, Jose Alberto, and others are all here. So yeah, I hope that you will enjoy it. Oops, where is the? Okay, so I'm not going to spend time here because it was explained in Rashid's presentation and mentioned earlier on by Jens. Spectral distortions are really a very fantastic probe, at least from the point of view of our understanding of the universe, because any energy injection leaves a trace in the CMB. So it surpasses by far all the usual probes that astronomers use, being it galaxy surveys, being it 21 centimeter, and in fact it's really equivalent to the CMB, allowing us to trace and test the cosmological model across its history CMB, temperature anisotropies and polarization are the traditional tool to do so, to trace both the structure formation and the early stage of the universe. And we think that the spectral distortions are a new observational window to this understanding of the universe. And in order to open this new window, we have put together very recently and submitted for a stage 1 step proposal selection for ESA M8 medium mission, a proposal called Fossil, which gathered already about 150 members, already beyond the small number of people joining WMAP. A very exciting representation of countries from Europe, of course, but from other neighboring and friend country, with a nice representation of the distribution of ages. So we thought initially that this would be something that would interest essentially, let's say, middle-aged CMB people, and we were very happy to see that early career scientists and PhDs are constituting about 60% of the proposers as of now. So what is Fossil? It will be the first full-sky, low-resolution absolute spectroscopic survey after COBE, with similar frequency range, with about 150 frequency bands, a 4-year observation with 70% efficiency, 10 times better angular resolution, about 2 degrees equivalent Gaussian beam, and the 1,000 improvement targeted and hoped by Jens, covering all the frequencies that you see here with continuous frequency statement by NFTS, with the delta nu, that's the resolution frequency of 15 gigahertz. So the opening this observational window needs to have dedicated and very specific targets. So we have 3 main targets in terms of numbers. And you see here the differences and the sensitivity expected for Fossil. First one is to detect the monopole-wide distortions, 3 orders of magnitude better. This is the easiest from the point of view of Fossil, allowing us to reach values down to 10 to the minus 8. Reaching out to the relativistic correction to the Z effect would allow us to measure the temperature of the gas down to 1.3 kiloelectron-volt at tens of sigmas. And eventually, we expect to measure the mu distortions 1,000 times better than COBE, reaching a detection of the expected 2 to the minus 8 value at 4 sigma in a specific case here for our forecast, marginalizing over the high frequency foreground and allowing for priors at low frequency. So what all this will allow us to do is to target 3 main goals and additional science. The first main goal is probing the density perturbation, and I refer this to Jens' discussion. We will be able indeed to probe the small scales of the density perturbation at ranges where traditional CMB and isotropy cannot, where other experiment cannot, in really a unique window of observation, to allow us to probe the primordial bispectrum, constrain the origin of the black hole, and eventually, if there is any departure from the standard model prediction of mu, rule out the single field slow roll inflation. Our second main goal is to probe the dark sector. Spectral distortions are expected from dark matter decay, from their annihilation, and from their scattering with standard model particles. And I show here an example of dark matter particle, noted Chi here, interactions with electrons. And the spectral distortions will constrain the nature of the dark matter by probing these interactions. In complement with ground-based detectors, like direct dark matter detectors in some cases, and in some cases being the unique way of probing this, as well as trying to pin down and find signatures of the dark photon conversion. The third main goal of fossil is to probe the large-scale structure formation and evolution. So we know that there is an energy release from the collapse of the baryons in the and the dark matter and the formation of the cosmic web itself. We know that there is energy induction by the feedback processes, feedback mechanisms that we see here, 2 feedback models from AGNs, from star formation. All of it will leave traces, will leave the so-called Soniev-Zeldovich effect that has been mentioned earlier on. And the idea here is to have a specific measurement of the thermal energy in the LSS through the measurement of the monopole Y to determine the temperature of the hot gas at the level that we want to attain, that is 1.3 kiloelectron volt, would clean up all the potential range of feedback models and nail down the energy injected by the supermassive black hole, constraining them to the sub-percent level, which will have a very big impact in our understanding of structure formation and their evolution. Of course, by having this range of observation between 30 and 30 gigahertz and 3 terahertz, this can open a lot of additional science. We haven't mentioned here the synergies with all other observers, but only focusing on 2 of them, which is probing the cosmic star formation in 2 ways, by measuring the absolute intensity of the CIB at the percent level, and hence probing the cosmic star formation history, and by measuring some of the monopole emission of low resolution intensity maps in the far infrared, in particular C2, CO, and others, depending on our capacity and ability to distinguish between all of these lines, in order to, and at least these CO and C2 would allow us to peer in the cosmic star formation peak, that is the cosmic noon, allowing us to probe the redshift range between 2 to 3. Obviously, an experiment like fossil, although with low resolution, 2 degrees, would allow us to understand the dust property and to probe the physical conditions of the ISM. And you see here several models that cannot be distinguished because as of now, I mean, the sparse coverage of frequency in terms of bands do not allow us to make all the difference. Imagine a continuous measurement up to 2 terahertz, which will allow us to really differentiate between the models. And the measurement of lines in the galaxy would allow us to identify the conditions of the ISM through the measurement of some of the molecular gas of the photodissociation region, I mean traces of the photodissociation region or H2 regions. How do we want to and how do we plan to do this? So we plan to do this with this experiment here, fossil. It's a heritage from Pixie and Pristine, but it's essentially a heritage from all the series of far infrared and CMB experiment. Because you recognize here the setup of Planck, you recognize, that they're an FTS, which it's an inheritance from Herschel. There are inheritance from Arcade, from ISO, for the filter wheel. And all of it is this experiment that we want to pursue with a sensitivity of 0.7 Jansky per steradian, measuring the absolute intensity with respect to an internal calibrator here. So you see here the 2 primary mirrors, the calibrator, a filter wheel which allows us to have 4 modes of observation, half of them being for calibration and half of them for science. And a dichroic here, which allows us to split the band into a low frequency and a high frequency band, allowing us to reduce the noise at the low frequency and hence to optimize the instruments to target the mu distortions. The 4 focal planes, 2 per spectral band, will be equipped by multimodal detectors, very few of them. We expect to have 4 multimodal detectors per FPU working at a very low temperature, and we have several options. Our baseline preferred option would be the resistive bolometers that have been developed and are being developed at Goddard for the moment. We are not just sitting here writing a proposal. There is a huge amount of work which is done in the community. So we're preparing for fossil, and we're preparing it in order to de-risk the concept and in order to increase the technology readiness level of the subsystems. And this is done via many ways. One of them is the ongoing phase A study of BISU that was mentioned by Jens. These are technical activities which include the development of a breadboard model that will allow us to basically fake or mimic a bisou, which is a small version of fossil, and to understand the systematic, to test them and to understand better the full system. But there are many other experiments, as was mentioned earlier on, based on ground-based experiments which are being in place or soon to be in place. TMS was mentioned at IAC, and Cosmo will be detailed by Paolo earlier on. We think we should do it now. We should do it now because such a survey is timely. There was a question in one of Jamie Bock's slides. What is the next step for the 2040s? And we think that the next step for the 2040s is a step aside. It's a step towards spectral distortions. This will have a huge impact from the point of view of science, with guaranteed and with discovery potential. We think that it's coherent with the strategic plans at ESA, at national agencies. It opens up the future, really. It consolidates and materializes community leadership in instrument, in science, and heritage from all our ground-based experiments in CMB and far infrared. I wanted to show this here because that was the status when COBE was thought of in the 1970s. The big success of COBE and of COBE FIRAS, showing that the cosmic microwave background is a black body, but not quite. We're here in the, let's say, middle age of the 55, let's say, having so many activities targeted to de-risk, to augment the technology readiness, to build up the community, and to bridge with the heritage that many people who contributed to COBE could help us in order to achieve the goal. We think that the ESA call, the M8 ESA call, is really a unique opportunity for a spectral distortion mission. That would be a fabulous anniversary for CMB, let's say, space missions. And it's obvious that we do not want to wait for the so-called large 6 mission aimed at 2055. By then, I think that we will be a bit tired. By then, we might lose a lot of our young, early career colleagues and experienced ones, and the leap is too large. So I think I'll leave you with my last slide, if it comes.
You have to just press another time.
I press another time. And I thank you for your attention. We need you. We need experienced scientists who participated in COBE to help us shape the instrument and understand and anticipate the difficulties. We need the early career scientists because this is a long breath experience, and I'll be happy to take the questions at some point during the discussion. Thank you.
Thank you, Nabila. So there is time for one question while Paul de Bernardis joins us for his presentation. Yeah, that's it.
Okay, thank you very much for the invitation. I'll be back to Earth here. We have to start to do something really hardware-wise for this long development we expect to have on spectral distortions. And I speak about the Cosmo program, which is a spectral distortion measurement based in Antarctica, so ground-based. If you look at the two plots, the top one is the atmospheric emission in Antarctica, in our region of interest, and the bottom one plots the two largest spectral distortions, which are the Arcade XS and the Y distortion due to post-recombination ionized universe. And you notice the disparity of the orders of magnitude in the signal. So is this really possible to extract the monopole CMB from atmospheric emission at those levels? That's the big question. We think we have a strategy to do that, and that's what I'm going to explain. Let me say that this is the big issue with ground-based experiments. There are other issues like side lobe, Earth in the side lobes, the presence of a vacuum window in the receiver, the electromagnetic interference, so it's not the only one. On the other hand, ground-based experiments have the opportunity to experiment, and we need that. We need to do measurements because not every single aspect can be simulated in advance of such an ambitious measurement. So, and we have the opportunity to develop, to test in a significant environment, and in principle we can go after the largest spectral distortions. So this is the collaboration of the COSMO experiment, the Cosmic Monopole Observer, and it took a long time to convince the agency to fund it, and we have had now, after many years, partial success. We are funded all the way to the commissioning and the test in Italy of the instrument, and I speak about that. So it's based on a Martin Paplet Fourier transform spectrometer, as FIRAS was. There are two input ports. You compare the sky to a cold calibrator or reference. The instrument is differential. You have to calibrate it, and this is the hard part. I'm not going through the details, but you can do it either by looking at an external black body or changing the temperature of the internal black body with pros and cons that we have to understand by experimenting. We can cope with the window emission, which is a big issue here, with a special procedure involving stacking two windows and comparing. Also, the key is to change the temperature of the different emissive components we have in the beam and see how the instrument reacts during the measurements. This is the other strategy we have to cope with this kind of disturbing emissions. So for the atmosphere instead, we are planning to scan fast. We use fast detectors. So we basically perform fast sky dips to measure the atmospheric emission and to remove it quickly. So not only the stable emission, but also the slow fluctuations of the atmosphere monitored and removed. And during this gives you an idea of how fast is the spectral measurement. We scan in a full interferogram in a few seconds. Meanwhile, we perform many sky dips so that in a single interferogram we have information from all the elevations. So we sample different atmospheric depths. We can retrieve with a standard sky dip extrapolation the external emission, external of the atmosphere, as long as we are able to model properly atmospheric emission. Simplistic forecast in 1 or 2 years of observation, depending on the efficiency of the observation from Dome C, we should be able to do this, which is in principle would be wonderful. But of course, there are foregrounds. And we have to carry out end-to-end simulations. This has been done. And the result is that we can measure the Y parameter down to something like 6 or 7 sigmas. So that's promising. Now, in a nutshell, this is the design of the cold part of the instrument, and my message is that we have already parts which are working. This is the scale scanner, spins very fast in order to do what I described before. While we scan the interferograms, we look at the different elevations so that we can sample atmospheric emission. We do have a big cryostat to include the Fourier transform spectrometer. We have the interferometer itself, all the beam splitter, the filters, the polarizers. We have a working variable delay line which has been tested at cryogenic temperature now with demonstrating negligible heat loads on the cryogenic system. We are doing our measurements on the cryogenic black body, and multi-moded feed-on arrays have been developed to measure the interferograms. We have 2 focal planes, each with 9 multi-moded detectors, which are kinetic inductance detectors, which have been developed to have larger throughput. This is something we have been developing since several years. This is the small team developing detectors, not just those, but these are the happiest ones. And we have flown these detectors in 2018. We have demonstrated their performance in near space. And I cannot resist from showing a press release which was out yesterday about our 90 gigahertz camera at the Sardinia Radio Telescope, which is completing commissioning now. We have a 64-meter dish, and we are detecting several great images of iconic sources in the sky. You recognize Orion, you recognize M87 and Casei. With changing from 1 beam to 400 beams has been a big step forward for the Sardinia Radio Telescope. Recently, we have been funded by the Italian Fund of Science with a good amount of money all the way to the test of the instrument in a relevant environment. So we have the money to insert the hardware you have seen before in a shipping container so that we can bring this container in this site, Campo Imperatore, 2,200 meters near Rome, and do our test in 2026. And following this positive test, also the Antarctic project is planning to accept the instrument in the Concordia station we have in Dome C, Antarctica, where things will be favorable for this kind of observation. So my conclusions are that I'm for a phased development of this instrument. We heard about the most ambitious plans, but these had to be preceded by high mountain, maybe Antarctica afterwards, then a balloon, and finally space in any possible way. Dome C-based measurements will optimize the instrument, will allow us to play with fast sky dips, with the side lobes, with the calibration procedure, which is the most difficult aspect of this measurement, with data analysis procedures, and will this will complement low frequency efforts. TMS is important, will work at a much lower frequency, but it's important to have a coverage of the spectral signal we are after. Can be sensitive enough to detect the largest spectral distortion, and as a complementary output, will be able to characterize the dome C site at millimeter waves with a very thorough characterization, and also will provide environment relevant data on the content of ozone and extremely low levels of water vapor during the Antarctic winter. So that's a complementary important output of the experiment. Thank you.
Thank you, Paolo. There is time for a question. Well, we'll ask Joe Silk to join for the next presentation. Julian?
Will be on a elevated platform. Not too much, maybe a few meters. Yeah, depending on the weather. During the winter is a bit different.
Okay, so now for something completely different, you could say. I would like to explore what is possible in the future, something totally radically new in the CMB, but with a guaranteed science return that is so compelling that I'll hope to persuade you by the end of my talk, this is where we're going to be going. And just to begin this, it is long-term science I'm proposing, but I just have to alert you that if you look around us in this town anywhere, you see some wonderful old cathedrals, Notre Dame, whatever. The architects who built those were not alive at the end to see their results. And in some sense, the science I'm going to tell you about is for the youngest people in this room who will be there to see it in maturity. Because we're talking timescales of 40 years, 30, 40 years. Anyway, so let's begin. My collaborator, Jean-Pierre Maillard, unfortunately is ill. He's done most of the work in this talk. I've supplied a bit of theory. And this really is essentially his ideas. So the idea essentially is to put an imaging Fourier transform spectrometer on the moon. Now, where would you want to do this, and what is the idea? Well, it's going to be, in principle, something like this is from Nabila's schemes for various smaller scale projects in space. But let me just try to give you the perspective for future missions. From the point of view of ESA, this would have to be a large mission to get the rewards that I want to explain to you on spectral distortions. And so we have a busy calendar in large missions, and my best estimates, given what lies ahead, is that we might have a slot in 2065 to pick up on the Voyager 2050 request that we consider spectral distortions as a future major goal in combination with a possible, or in competition with a possible gravity wave experiment. So that we've heard on the NASA, on the ESA side. On the NASA side, I'm not going to say anything more about their flagship missions. There might be openings for a probe class mission, but so far the example of that proposal was PICO, which essentially had a minor spectral distortion component, but then dropped it for funding reasons. So that, I'm not optimistic, given the US community, that that will be our future in terms of free-flying space missions. That could change. But what we do have immediately, with immense funding behind it, even now, is the Artemis program. And so we're looking for planning, which is sort of guaranteed to 2027, and after that, to be seen, but that's way beyond our present US administration. So all this is likely to go ahead. And again, the main driving reason for this is China. So China is the competition, and I think in general NASA is determined, and the US is determined, to get crewed missions onto the moon before the Chinese do. And they've said they'd do it in 2030, and I'm sure they will keep to that word. So right now we have a window, 2027 and beyond, and the next decade for future extensions. So all of this is wonderful, but what will the astronauts be doing on the moon? Well, why not? Why don't we have them put down 1 or 2 telescopes? That seems to be an obvious sort of project that you might want to start with, in doing exploration on the moon. And so that is basically behind this philosophy. And so what then is the advantage of going to the moon? Well, the lunar sites are essentially unique. Without an atmosphere, you get access to all of the electromagnetic spectrum, ideal for infrared, far infrared experiments. And if you go to cold, dark craters, which have limited fields of view near the poles, and they're incredibly cold. The ambient temperature at the base of the crater is 30 Kelvin. It's also, there's lots of ice there too, which is useful for various other things, such as that would be useful in local manufacturing or whatever you want to do in the moon. So all of this looks promising. And so what you can do is ask, where are such craters that you might want to install your potential telescopes on the moon? And there aren't that many. You have to go near the poles, and the reason is the sun will never be too high or too low, below or above the horizon. And that means the temperatures rest modest, and then the craters are deep enough with high enough rims so they're permanently dark and permanently cold. So wonderful places. There are dozens of them. We're exploring now the south pole of the moon. That's where the Artemis program will be going. So that's the first site we might think about. But there are craters around the North Pole too. They're equally interesting. And this shows an example of a couple of craters we might consider. The Shackleton crater, well explored. Notice the high rims. Light all the time because the sun is essentially illuminating the tips of these very high craters, even when it's slightly below the horizon. And so that, and another even larger crater at the North Pole. And so you have lots of space there, great temperatures to do in astronomy type things. Okay, so where did this project I want to describe to you come from? Well, it was the brainchild of Jean-Pierre Maillard, and he proposed this at a couple of meetings that I organized in London in the past 4 years on astronomy from the moon, the next decades. And the question he raised was, is the moon the future of infrared astronomy? And I'm going to argue in this talk that it is, because it'll be great for all the spectral distortions you just heard about in the preceding talks, but also for the recombination lines from the recombination epoch and just before. And that would be an amazing thing to do, and that's guaranteed to be there if we believe in the Big Bang at all. And the basic project's an array of 4 1.5 meter telescopes, basically 4 units feeding a Fourier transform spectrograph detector in one of these permanently cold lunar craters. Okay, so there are other things you can do on the moon. These are even longer time scale things. I'm sure they're going to come, but for example, you'll do imaging in regions where you cannot access very easily from the ground, even in space. You'll have a hard time building a large enough instrument. On the moon you can do this. You have a very stable platform, and ultimately we'll have kilometer-spanning telescopes that will give us amazing resolution. This would be combining beams Arecibo style with a focal plane suspended from the rim. So that's all very futuristic. That will come, but the time scale there is probably longer than even for the youngest people in this room. But nevertheless, it's something that we really should be planning now or it will never happen. Okay, so here is the basic line. What are the gains that you can get? So in addition to this table of gains, I have the optical layer. I'm not going to address that at all. It's not so different from what you heard about already in the previous talks. with an imaging Fourier transform spectrometer. But if you look at the gains on the top, it's relative to PIXI. So PIXI, a wonderful experiment designed to look at recombination lines, rejected twice by NASA in the MEDEX program. And we can be optimistic. The new proposals may have better success. But the problem with it was it didn't get down to a definitive detection of the mu distortion, which is the one guaranteed signal we have from the early universe and would be a wonderful test of small-scale structure and cold dark matter. That's the first thing you want to go for. And so how do you do that? You have to beef up your gain, and you can do that in various ways. You can add more detectors. PIXI had one single detector in the focal plane, and then you can have a larger telescope and etc. and various other tricks. So you can imagine beefing up the gain by a significant factor, perhaps as much as 100, okay, or certainly 10, in a future design for something. So why is this going to be so hard? Well, here is the optimal design that we have in mind. You'll have 1.5 meter modules. They'll be fixed. These telescopes don't need to focus. They just point at the sky, and as the sky rotates, you do circles, large bands of circles in the sky, and with 4 you get 4 adjacent circles. And so that's the sort of thing you might want to do. On these rings, you use the rotation of the moon to scan the sky, and then each of these units will be equipped with an imaging FTS, and it will be cryo-cooled to 2.5 Kelvin, which is fine given the ambient temperature is 40 Kelvin. It shouldn't be a hugely difficult challenge and would span the usual range that we're looking at from 90 gigahertz on upwards to the terahertz range. Okay, why is it so difficult? Well, first of all, we need a launching vehicle which can include these units in its fairing. That's something that I'll mention in the next slide. We need a lunar rover to deploy all this near the landing site. We need solar panels on the crater rim to provide power. That's great, going to one of these dark craters. We have the solar power there. And then we have to persuade the powers that be to start thinking about a schedule for this program, which certainly they're not yet. Okay, so that's the basic idea. Now, why would you want to do this on the moon rather than follow the Voyage 2050 recommendation of a large recombination line target mission, actually spectral distortion mission in space, which was discussed. As I said, one reason is the date. The timescales are now the same if you want to do this as a free flyer in space or doing something on the moon, because we are basically exploring the moon the next 2 decades and doing experiments there. So those are similar timescales. The budget's an issue. Well, if you want to do a large free flyer, that's going to be a real problem budget-wise, especially now to have, you're going to have to span them out in time. Fortunately, the lunar programs have very high priority and enormous budgets in principle available, and it's certainly time that astronomy tapped into those more effectively than it has done so far. That's beginning with the first experiment to look for the dark ages. It won't get them certainly, but it's flying at the end of this year to the far side of the moon. That's Lucy Knight. So it's all beginning, and we can do more than that in the near future, I'm sure. Okay, so another advantage of the moon is it's much simpler than going to L2. You don't need propellants or anything. There's no limit on time. We have in this simple scheme 4 identical units will be used. The acronym for this is multi-SIMBIRD. But here is the big change. In all we're doing on the moon and beyond, we suddenly have access to rockets with huge internal fairings. So basically, this shows you the history of our large rockets, and Starship and New Glenn will have internal fairings up to 9 meters in diameter and up to 20 meters in height, and can take a payload to translunar injection of many tons. Now, you may say this is incredibly expensive, but here is the big wrinkle on this. The SLS mission, which NASA is using to get our crew to the moon, is $4 billion per launch. It's incredibly expensive. However, Starship, courtesy Mr. Musk, and likewise New Glenn, no doubt, is recyclable, and they are promising numbers on the order of $100 million per launch. This transforms things completely. It's no different from a Falcon 9 cost of a launch to get to the moon now. We did that with Euclid, etc. Similar sums are involved. So the landscape is really changing for getting big, heavy experiments on the moon, as long as they're not too complicated for the astronauts to have to run. If indeed we need crews at all, which is another question. Okay, so what are we going to do scientifically with this? So this is the basic outline of sensitivity to spectral distortions. So you've seen versions of this already. So you'll notice that we have Kobe fire ash result plotted there. We have the Pixie goal plotted. So the Pixie goal could not quite tackle the mu distortions, which you see in positive definite units. That is a dip on the left, a rise on the right. And so you have to do 10 or even 100 times better than Pixie in sensitivity. That's the ultimate goal. But if you do that, not only do you get a high sigma detection of mu, and let me say the mu distortion is a significant test of the cold dark matter model of structure formation, because the mu distortion energetics comes from the dissipation of small scale structures, the damping effect, but on small scales that we haven't seen yet, but predicted to occur in the very early universe between, when the black body radiation was last distorted, which is around a few months after the Big Bang, up till tens of thousands of years. We can probe that for small scale structure with mu, but we can do even more if we can boost the sensitivity. And so these are the recombination lines that you want to get to. Hydrogen and helium first, but amazingly, helium, I show that as well. Is this realistic? Can we ever get there? If you could, it'd be the most amazing science you could do, I think. Okay, well, this is the projected Voyager 2050 sensitivity from a white paper on the internet. And there's no doubt that one could do the same thing with the multi-Simbad models on the Moon in a dark crater. So one could get this range. And depending on how complex you make this system, how you detect, etc., you can really work your way through that yellow band. And you'll notice that suddenly it's not just the hydrogen helium recombination lines that you can measure, but even the helium lines. So this will be such incredible astronomy in the first few 100,000 years of the universe, the same stuff that's our bread and butter today for all of astronomy, but now projecting to cosmology. To me, it's such a compelling science argument that no sensible committee would ever turn this down. But of course, it's going to cost something. And there are no doubt technical issues. What I haven't said is the foregrounds are enormous. We know that already. But having a nice wiggly line spectrum is going to help you a lot beating down those foregrounds. You know what you're looking for exactly. And so no one has really modeled this yet to see how well you can do. But I'm optimistic that one can make a case for progress on that too. Okay, so let me conclude. The moon, I think, is a really promising site for infrared astronomy in the next decades. It's the temperatures are right. The sky coverage is limited in these dark craters, but so what? You can do a lot on small patches of the sky, and it's got a wonderful opportunity for the CMB for doing spectroscopy, which I think is the ultimate goal. And if we want to, build our cathedrals for the future, we should be persuading the youngest people in this room to start thinking of the very long term and join in with these experiments, because they will be around to see them to maturity. And I think that's a very exciting prospect. So that's all.
Thank you, Joe.
Thank you.
Thank you, everyone. So now, of course, we proceed to questions. We have one already.
Yeah, just to directly follow up on Joe's last remark. So nobody would ever turn this down, and that's true that ESA's senior committee for Voyage 2015 had a full endorsement for recombination line science. Everyone was sold, right? That's why they made a recommendation. Science case was unquestionable, unanimous support for this science. So they made a recommendation. But now I'm a bit puzzled because then you ignored it. They try to do other ways, right? So of course, these are probably parallel efforts, but I hope that because the current situation is ESA asked communities to do the homework, then come back to them to initiate expert review. This hasn't happened for the spectral distortion and also gravitational wave community that's in competition. Nonetheless, gravitational wave community is in preparation of writing a white paper and submitting to the ESA. So that's led by Alessandra Bonanno and Geraldine Servant in DESI. So they are doing this, right? So on the other hand, this fossil is a wonderful thing. Of course, I hear from multiple people that just going full swing directly to Voyage 2050 is just risky and it takes a long time. But I think you should talk to program office of the ESA, because if they think that this is what you want and you get it, there'll be no Voyage 2050.
Okay.
So I think, but you just have to talk to them, right?
Yes.
So if you do this without talking to them, then maybe that's okay, no? Then you have MA, that's wonderful.
Sure.
Then you go to the moon, that's fine, right? So, but I just wanted to tell you that ESA is waiting for your.
Well, thank you. I mean, I thank you also for your contributions to Voyager 2050, which set a lot of this in motion. I think that it's time to make a much harder push for reasons I don't fully understand. We've been distracted by, the very wonderful goal of going for the tensor to scalar ratio in our future experiments and analyzing all that to death, I would say, and that still remains a very important goal. But to get to the lines I talked about, you have a very bright foreground. So, and you have to work your way down to basically nanokelvin or less, but we've done that. We did that with the CMB, okay, already. So the next barrier is not microkelvin, but nanokelvin in our future experiments. So I don't see why for the spectral distortions, with this wonderful aid from knowing exactly where to look in frequency space, I think theorists should be investing much more time in working out, signal to noise issues, how realistic this may or may not be. But we've done it before with the CMB. We've beaten down huge foregrounds. I don't see why we shouldn't be able to do that with the infrared backgrounds or whatever that are blocking this at the moment.
Can I continue on this? So thank you very much for the comment and for the advice. Indeed, ESA is really late in terms of the implementation of its program. They just started now to put up the study teams for the L4 mission. That is the one which is after JUICE, the LISA and Athena. It's Enceladus mission. So just started now, okay? So if we wait for ESA to start activities, that might indeed take a lot of time. I think that we have been discussing, not with ESA officers, because by proposing a mission, there are conflicts of interest that you have to take into account. What I want to put here forward is the fact that we need and we have a roadmap for spectral distortions. It was highlighted by Paolo. We need to have ground-based experiments, and this is what's happening now. It is happening. There is COSMO, there is TMS. We need to have balloon-borne experiments, and this is happening. There is a phase A BZOO. We need to have an intermediate science mission, and I'm not talking about a pathfinder, okay? We need an intermediate science mission from space, and this is fossil. And then we need to have a big thing, the thing. And this is something that can be either an orbiter in L6 or a facility on the moon. This is the roadmap. What we do not want and what we cannot do is wait for step 1 to finish and then start step 2 and then step 3. That's not possible because we will just exhaust the community, exhaust the ideas. And I think that we can take example of the Martian program. They have such a roadmap. They started with orbiters, then in-situ observations, and now sample return. We have the plan.
Yeah, but that plan is shared with Lisa. That's what I'm trying to say. So they don't want.
Please.
Yeah, actually, they made pretty explicit that they don't want intermediate M-class mission for this.
They don't want Pathfinder missions.
But it's the same thing. But you should talk to them. I mean, I think everything is on the table, but you just have to talk to them.
Mm-hmm. Yeah, no, thanks you very much for that, for sure. But I would really like to say that I think that a lot has changed since the Voyage 2050 study. We have now seen a lot of new things like JWST. I mentioned a few just indications. We have opened up the window to gravitational wave backgrounds, stochastic backgrounds. The universe is really interesting at small scales. Mu distortions and the recombination lines, for that matter, they can help you with studying the universe at small scales and in the very early phases. Completely complementary. We are missing out on a lot of great science that other people are now doing and starting, and we will be able to put numbers on the chart that are so primordial, no other experiment can actually put numbers in that way on the chart. There will always have some modeling of astrophysical evolution, knowing where the sources come from. If we see a mu distortion, it comes from the early universe, which is a really amazing, important contribution in this complementary multi-messenger and multi-frequency approach. I think that has really significantly changed.
Yeah.
And if we are missing out on that,
but
it's going to be really.
They are sold on science already. You don't have to convince them again.
Okay, so
what hasn't changed is the money.
Yeah. I mean, when ESA embarked in LISA, they spent 600 million euros in LISA Pathfinder because they needed to have so this is the type of
that's exactly why they don't want to do this again. But you have to just talk to them, and you don't have to convince them of the science. They are sold, right? So just
So please help us and talk to them as well.
I wanted to add there as well that it is really important because also in the earlier session it was said the CMB community. In reality, spectral distortions are part of the CMB community, and we really need the help of the CMB community with, for example, preparing for these steps, which is not happening, I must say. And it's not happening in direct ways. It's happening in some, with a small group of people. But it's also not happening in terms of, funding and initiating activities as much as it should probably. And it is great that we have now these activities from the ground, which are really, I think, a key milestone in making a transformation in that kind of, perspective, which is really amazing. So I just wanted to add that.
So I have a small curiosity for Joe. So the moon doesn't have an atmosphere, so that means that there is a number of meteorites reaching the surface. So do you have an estimate of the time scales for the deterioration of the optics of the telescope, or you have already a solution for that? Or?
Well, so the quick answer is the Chinese did it already. So around 2014, they landed a telescope on the near side of the moon, but a region that gets very hot in the day, very cold at night, etc. They put a mylar screen over it, and it worked for 10 years, sending back beautiful images. So that was optical near UV. So I think it's been demonstrated that the regolith and the conditions are not a huge obstacle to doing things on the moon.
What about that?
Sorry, that was exactly, when I once discussed this not so long ago with someone trying to push an optical interferometer for the moon, the response was, there's so much dust, it'll never work. But China did it. They showed things work. So...
One step back to the previous discussion, I think it's fair to say that submitting a proposal to ESA is a way to open a dialogue with ESA, because they will have to respond. At the same time, it's also fair to say, I believe, that one of the reasons spectral distortion science was not considered as a viable science for the empath was that at the time it was felt it was too costly to fit in an empath. Now, if this has changed and if people are convincing in demonstrating that you can do science and not Pathfinder kind of exercise on that, the situation might well change.
Okay, I can take it maybe. So I guess you're referring to the proposal that was put for the last call, the M7, 3 years ago. So so first of all, let me answer to the first part of the question. Not a Pathfinder, but science. I mean, we hope that we have indeed shown that we are going to reach several hundreds, up to 1,000 improvement in sensitivity, provided the very big challenges and exciting challenges of controlling systematics and everything. And this will allow us fantastic science. I mean, we're talking about other communities who have incremental improvements, okay? That's for one. So we have the science, it's not a Pathfinder. For the question about the cost, what happened at the last submission of proposal is that we have costed, in terms of the contribution to ESA, parts of the payload that were not that ESA was not ready to take. In particular, just to make it more specific, we have a very complex cryogenic chain because we are inheritance of Planck, and there is a so-called 4K stage, 4 Kelvin stage, which at the time we put the proposal M7 was not at all included in the developments that ESA is doing now. So ESA is indeed, in this call, the M8, is indeed announcing that they are going, or they can take into account, under their contribution, the development of a 4K cooler, which is necessary not only for fossil, and they don't do it for fossil, but they really feel like they want to have some, let's say, independence, or I don't know how to say it properly, with respect to collaborators. And this is indeed included in the cost and should be covered, which was not the case last time. Enfin, that is, we put it in there, but it was not anticipated by ESA. So we hope that everything is fine. We'll see.
So here's another response. ESA obviously looks promising, but I'm worried about the scale and the time scale. But NASA probes offer another option. This failed with PICO for the following reason. The spectrometer was a subdominant science component and was dropped for cost-cutting reasons, as I understand the story. Some of you may know better. So I think as we come forward in the next decade to propose a new probe, I would say if the CMB community got together and chose spectroscopy rather than imaging, that could be a way to go. But I have no idea what the prospects are for doing that. It's a minority, view at the moment, I think.
So just a clarification, FOSSIL is a proposal which is put together with US colleagues from the East Coast and the West Coast, and we have a significant contributions from NASA. From US colleagues, let's say NASA. We'll see, depending on what happens in the future. But
a great challenge for this kind of science is going to be foregrounds, galactic foregrounds, and in that sense, I mean, there's something partially in common with what the community is doing on, polarization studies. So, and I think it's going to be important for going to this, 10 to the minus 7, 10 to the minus 8, show the credibility of actually reaching those levels given the galaxy we are in. So how would you comment on that, and what can the community do? Maybe there is some sort of coordination in the work that can be done starting now in that direction.
Well, starting now, I would say it's BIZU, balloon projects, Paolo's, to get data on the foregrounds and then, basically dissect that data to death until you figure out a way to go below those. So I think that's the first step. But balloons should be an entry into tackling this, I think. But my colleagues may have other views.
So, of course, that is one of the big challenges, and it is something that I think we have really done many steps to actually improve on. And I just want to, given the challenge of the foregrounds, that was one of the reasons why the moment expansion method was put forward. And I think you can see how the synergy and the overlap in terms of like applications of these things are indeed indicating that we should be really thinking about this kind of question together. And even the combination of existing imagers, future imagers, past imagers, all that legacy, all that, uniting all the data sets, basically stripping away the low redshift universe by combining everything, which on a 20-year timescale will probably involve machine learning and all kind of methods that we are all dreaming about in the R science as well. So I think demonstrating that all that will work in advance is just the same challenge that the B-mode people are facing, and I think we will need to basically face that challenge together in that sense. And I think together we can really make that happen as well by realizing that this is not so different from what B-mode science has been doing. And we also have the anisotropic spectral distortion science, which is just in some sense one way of realizing the synergy again in that respect. So I think the answers and the ways to solve these problems will be given, and are, we're working on it.
Yeah, if I can continue on this, it is already happening. There is people who are working on foreground cleaning, foreground modeling, foreground simulating for imager or imaging mission. They are the very same people who are involved in the preparation and the construction of the models for spectral distortions. But what I take from your point is indeed it is at the level at this stage it's at the level of individuals, and maybe what we should do indeed is have like a visibility with a coordination, because it's already starting and we're not inventing things. Although for the component separation, there might be specific techniques to be developed. Some of them have been the moment expansion that you've been suggesting, or the least response method that you guys have been proposing also with Dmitry Novikov and others. So there will certainly be specific things. But you're right, we should give more visibility to this like overarching thing, which is a commonality to both.
And the Cosmo-Globe framework that was discussed yesterday of course comes to mind there.
Yeah, definitely. Yeah. Which include FIRAS, by the way. Sorry.
Well, just to add that you remember, Marco, how we combined the Planck data and FIRAS data. That is going to happen more and more, and every single bit of data we gain with preliminary experiments will be analyzed in that way, will be very useful and very important for the prosecution.
Thank you. My question mostly to Joe, and maybe Jens can also help, is I want you to clarify the CDM physics, which you mentioned about this very early time, that you can probe through this spectral line, of this spectral distortion. Are you probing some of the non-standard CDM, means if they decay or they interact some way, or is it just a typical non-interacting CDM that still have some physics that you can probe?
Look, in this meeting, we've been discussing challenges to the standard model of cosmology. That just won't go away. So the first thing we need to do is verify or find other problems with it that are more fundamental than the current debate about the expansion rate of the universe. And I think going very early, where the universe should be incredibly simple, and looking for these recombination lines is a great way of testing physics. Eventually, as I think Jens has shown in one of his papers, just studying their details and their excitations and their detailed ratios will give you immense information about physical conditions, a few 100,000 years after the Big Bang. And that's what we need at this point, to have confidence in our basic model.
Okay, I have a brief comment. This goes back to the slide that Jan Shloba showed and mentioned Apsara. So I just wanted to say the primary PI there, Mayuri Rao, joined as a faculty a couple of years back, and we have a cold receiver lab. A deployment has happened in our field station. We hope to go to the high altitude sites. So this is something that's happening, not in a big way, but it's something that's on the way.
Yeah, I would have had time to mention it explicitly as well. I think this is also extremely interesting. It's also targeting the low frequencies, and there is opportunities to do some of this from the ground with a rather smooth atmospheric, contamination as well. So this is really interesting as well. Yeah.
Yeah, and sorry I didn't mention, but indeed I was mentioning our US colleagues and friends, but there are Indian colleagues and friends who had signed up for fossil and very interested also in the technical and science aspect. So that's really a super cool thing.
So I have a comment in relation to what Marco was saying before on the modeling of understanding the foregrounds for the case of the monopole. I think, well, it was mentioned already by Jens, it was mentioned in the other talks, but we should not forget that the synchrotron monopole is a new background. It's the only background that we are not understanding. This is not attention. It's a real signal that has been measured by Arcade, has been confirmed at low frequencies. It's a factor of 5 above the prediction from the number counts of objects that we are able to count individually. And people in the particle physics community are very much interested on the fundamental physics that can be done already with the characterization of the synchrotron background. So that's a comment on that.
Yeah, and that is science that can be targeted with TMS, of course, as you are proposing, and with Bezout as well. And indeed, it is a curious signal, and it's actually interesting that we're not talking about it more, because I believe it really indicates towards, it shows that there is early activity, probably radio loud rather than X-ray loud, very, very enshrouded black holes. Even JWST sees that there's sources that seem to be UV quiet or more UV quiet. I mean, this is all very interesting early universe physics and structure formation physics, of course.
So if my memory doesn't fail me, when Al Kogut was writing his last version of the Pixie proposal, correct me if I'm wrong, it argued that with its spectral resolution essentially near absolute calibration, it also offered imaging, and in fact talked about, if I'm not mistaken, polarization. So that all put together sounds like, with 2-degree beam, like Lightbird on steroids. And is that in the fossil framework, or has that been lost in the process, or was that overestimated as a capability at that time?
So in terms of imaging, there is the capability of imaging with the 2-degree beam that we have. So that's we can have maps at 2 degrees. We have made a choice to target the science goal to spectral distortions. So it is possible technically to choose the detectors so that they are polarization sensitive. This has drawbacks or impact in terms of the scanning strategy, in terms of the calibration process, just to ensure that the systematics are okay. It's not our choice because we don't want the usual Christmas tree mission syndrome, and we targeted to spectral distortions. Also, because there is all the activity on polarization, which is ongoing on the ground with Lightbird, which is targeted to polarization. So we think that there is a huge complementarity between those two space missions. I mean, seriously, I'm not saying this just for like whatever. There is a huge complementarity, and I think that both of them should be targeted and to their goals, because you cannot think of a mission for two so complicated goals. So that was the choice that we made for fossil.
When Planck was proposed, there was no polarization on it, and the case was added, and we don't know if Lightbird's going to happen, and we don't know if probe's going to happen, so the question is capability.
Yeah,
so
we don't know, definitely, which is what I said. there could be the possibility to include a polarization sensitivity possibility to the detectors. It's not our choice, definitely.
And I would also say that it's clear that the community has actually spoken strongly against that combination. And I think we don't need another competitor for R on the landscape. If anything, we need consolidation of experiments and a focused plan towards R and also spectral distortions. It would be great if that would be something we can do together and really join, where the spectral distortion mission part is not optional and will be erased at the last place, but actually where we are, saying this is the optimization. But I think these are two different platforms, as Nabila was stressing. These are different concepts, these different approaches, and I think we're just not. I wouldn't say that that's actually really a possible, feasible direction.
Yeah, I think I would like to stress what you said. We don't want a competition in a community, CMB, which is small with respect to the other communities that are playing on the same competition.
So the last cynical remark, that we sorted out really seriously in the community, because I remember some years ago when ground effort was taking off, we've been explicitly advised in the dinosaurs of space community not to speak too loudly, not to dampen it, because it really needed to grow. Now we are 10 years later, and we're talking about morphing still unfinished ground effort into finishing touch with space on it, so the goals are achieved in a realistic and interesting time. So I don't know how that consolidation of communities is going to go.
Yeah, we don't know neither, but for the moment we have a science target and an optimized mission for the science target.
Okay, so we have time for one more question. 1, 2, 3. Okay, I think we are done. And thank you so much. Interesting discussion. Thank you.
Stay here for the picture, just a few minutes. Right, group picture.
So he's in the room. He's here in the room.